fourth session of the Mathematics and Online Learning Workshop. I am happy to introduce Naman Agarwal, who is from Google A Princeton in Alaa Dizan's lab, and he's done lots of good work on online LQR and online control, and I'm really interested in hearing your talk. So please take it away.
Thanks, Alan. Thanks for the introduction. Thanks for inviting me. Let me just share screen. Can this be seen?
Yep, I can see it.
Okay, sounds good. Okay, thanks for coming to the talk. My name is Naman. I plan to talk about this framework which we have been sort of thinking about at our lab for a couple of years now. We call this the Non-Stochastic Control Framework. The work that I'm going to present today is a year and a half older, but hopefully that's kind of the work that sets up the other stuff. So hopefully I hope to convey some intuitions, and I'll make pointers to other work which might be interesting to folks afterwards. Okay, so let me begin by just thanking my collaborators. This work was joint work with Brian Bullins, Elad Hazan, Sham Kakade, who was visiting us then, and Karan Singh. Okay, so what is this about? Well, it's about controlling dynamical systems, and sort of it finds this topic is age old and sort of finds applications new and old. Maybe newer applications include things like autonomous vehicles. In Google, there are things like data center cooling, which have found, like where control of dynamical systems have found applications. And sort of something that our lab's been working on should be released pretty soon is controlling things like medical ventilation in the present scenario. Okay. So what's a dynamical system? Well, here's a cartoon. Basically, it's anything that you can essentially actuate and you can control to sort of have a certain behavior that you wanted to have. Okay, so of course, control theory is an age-old field. What's sort of the motivation for our work? We sort of, I guess, our work stems from sort of like trying to think of control in the age of, say, machine learning. The sort of focus that we want to have with this work is kind of focus on sort of the notions of robustness, which we consider in machine learning, and sort of bring in the notion of simple algorithms like gradient descent, which are found to be sort of more robust and sort of efficient in this large data regime. Moving forward, one would sort of try and imagine things like nonlinear controllers based on deep neural networks and things like that. So these sort of form, so getting this sort of more machine learning focused robustness notion was the motivation for our work. So sort of without dealing it further, let me just begin. The first part I'm going to talk about this work, which appeared in ICML, should be 19, online control with adversarial perturbations. Let me just set that work up directly. So before setting the work up, let me define the notion of, say, optimal control of dynamical systems. A dynamical system is essentially governed by like a state equation, and the state equation has multiple parts. There exists a state of the dynamical systems, which is denoted by this variable x sub t. There is a control input that you provide to the dynamical system at every time. That's denoted by u sub t, and there is a certain perturbation that drives the system. Okay, so given x, u, and wt, the state kind of advances ahead with some known equation given by some function f, and sort of the goal in optimal control is given a certain cost function. You want to sort of a cost function on the state and the control. You want to come up with a strategy of controls or a sequence of controls to minimize this this cost over time. Okay, so I'm going to consider throughout this talk, I'm just going to look at discrete time systems. And in particular, the precise dynamical system that I will be looking at will be a subcase, but a rich sort of subcase of the general case of dynamical systems is called the linear dynamical system. A linear dynamical system, basically, the next state transition is a linear function of your state and of your control. Okay, so that's the setup. That's the problem that I want to look at. And sort of let me begin by sort of saying some sort of a very high level overview of sort of what's been done before. Of course, this topic has been studied since the 60s, since the time of Kalman. the most canonical result in this field is a controller called the linear quadratic regulator. And herein the assumption is that the perturbations that you get at every time point are, let's say, drawn from an independent Gaussian noise, independent across time, and independent of everything before. And the costs are quadratic. So they're quadratic functions of the state and the control input. In such a setting, it's well known that the optimal control law is a linear function of the state. So ut is equal to k times xt, where k is a matrix that you can compute, which depends upon the system itself. So it depends on a comma b. Okay. So just to sort of give an idea of why this happens, sort of the intuition is quite simple. It's about just writing the Bellman optimality equations. So if you what you begin with is sort of assuming that the value function at any time t. So from any time t forward, if you're at a state, the optimal value function looks like a quadratic in the state that you're in. And sort of if you expand this out one more level to solve the Bellman optimality equation, the value equation, basically you continue getting your sort of inductive assumption that the value function is quadratic, and you also sort of easily get that the control input is linear in X. Okay, so that's sort of a linear quadratic regulator. And one of the main assumptions that goes into the linear quadratic regulator that we sort of want to challenge in the work is the assumption of independent Gaussian noise and quadratic cost. So these are sort of central assumptions to get things like, so to get sort of this result about linear quadratic regulators. And sort of just looking at the aspect of removing sort of the independence assumption over noise, think people have looked at this before. And a notion that is very popular sort of in this field is called H infinity control, or sort of you can think of it as a min-max version of the control. So I want to be able to sort of say something in a worst case sense about WT. So what you do is to set up a min-max problem. So here you're sort of trying to find the best sequence of control inputs such that against any such that against the worst W1 to T, say an adversary might decide of bounded norm that this overall cost is minimized. Okay, so I didn't say this before. I'm going to assume that the initial state is zero, and then sort of the whole system is just driven by the control inputs that you provide and the perturbations that are provided through some process or through some adversary. And in H infinity control, you are trying to sort of guard against the worst possible adversary with respect to a single sort of input sequence. Okay, so sort of looking at control a little bit, it's kind of easy to see that, like, while the notion is extremely strong, its strength sort of makes it extremely pessimistic. So in some sense, what you're doing is you're sort of trying to guard against every possible bad sequence an adversary might provide. And in that sense, it is fairly sort of pessimistic. The second thing that kind of happens while this is sort of easy, that while solutions for this problem exist when the cost functions are quadratics, sort of when you want to go beyond quadratic cost functions to say general convex functions, which might come about because you might have some constraints and things like that. This problem tends to be computationally ill-behaved. It's not clear whether it's easily tractably solvable. So there are two sort of problems with H infinity control. It's pessimistic, sort of non-adaptive, and computationally ill-behaved. And these are the sort of things that we want to sort of target in via this sort of framework of non-stochastic control. So what we want to add to this story is to sort of add ideas from online learning, get some notion of regret or a regret analysis, something which is more of an adaptive performance metric, and something that sort of yields efficient methods for directly for something like general losses, something that's not specific to quadratic losses, something that leads to efficient methods for general convex losses as well. Okay. So sort of just to give you a sort of motivating example of why one might want to study something like this. So imagine you want to fly a drone from some source to destination. You understand your drone completely, but sort of there are unknown factors in the environment. There might be wind, rain, other uncertainties, which are clearly sort of non-stochastic, right? You should not expect wind to be stochastic in any way. And sort of what or like optimal control, robust control theory or H infinity control says is to plan sort of in a worst case sense of, over all possible wind conditions. Okay, so this is clearly overtly pessimistic. What if when you sort of try, when you go on to fly your drone, what if there was no wind? Or what if wind was of a very particular structure that you could have sort of taken advantage of? Okay, so our goal here is to sort of get some notion of adaptive control, which sort of gives us the best of both worlds. We want it to sort of be optimal and fast when the weather permits, and sort of be also optimal to sort of instant perturbations, but also it should not sort of go extremely bad when sort of you hit that sort of worst case, which H infinity control guarantees against. Okay, so we want to get finite time provable guarantees. And for this, we will sort of introduce this online game, which I'm going to define next, and define an appropriate notion of regret, which will sort of capture some part of H infinity control, and which will also be hopefully more adaptive. Okay, so let me just sort of set up the problem. So just to define it again, so this is what we call the non-stochastic control problem. You've given a linear dynamical system that evolves according to this following equation, and you want to sort of come up with a sequence of controls so as to minimize this cumulative cost. There should be a summation there. That's a small typo. And sort of the salient aspects of the problem of the setup that we want to care about is that we want these costs to be convex, general convex functions, and we want to make no assumption about sort of the way the perturbations or the noise is being generated. So in particular, it could be generated by an adversary and such things. Okay, so just before I move on, let me just make some clarifications about the kind of thing which we are going to assume. I'm going to assume for the rest of this talk that the system is fully known. So I know the matrices A and B. I'm also going to assume that the system is fully observed. So I'm going to assume that you can have complete observation about the state X sub t. And I'm also, of course, going to assume that the system is time invariant. So the system does not change with respect to time. There's no AT comma BT. It's just A and B. Given these assumptions, let me just make a small point. If I've assumed that the system is known and the state is fully known, you're the one who is deciding sort of the control input. So I can, without loss of generality, assume that the perturbations are fully observable as well. Okay, so from this point on, I'm going to assume that the perturbations W sub t are also fully observed. Okay. So let me set up the online control sort of this online control of LDS or the non-stochastic control framework that I've been talking about. So let me set up this in terms of an online game. So imagine there are two players in this game. There is a blue player and there's a red player, and there is a dynamical system that's given by the state X sub t. At every round t, the blue player plays a control, say U sub t, and what the red player does is that it reveals a cost function. So it's an online game, so it reveals a cost function that has two arguments, the state of the system and the control input that the blue player is providing. Okay, so that's what happens at every round t. And after the two players have committed to sort of their particular strategies, what happens is that the system evolves. So the system evolves via the known system equation. X sub t plus 1 is equal to A times X sub t, B plus B times U sub t plus W sub t. And the blue player suffers the cost produced by the red player. So the blue player suffers a cost of C sub t acting on X sub t and U sub t. Okay, so that's the game. And this goes on for t rounds, as is typical in online games. And sort of what we want to do in this setting is to attack a notion of policy regret. So let me just define what the notion of policy regret is. I mean, we are not defining this. This has been defined before. What you're basically doing is you want to minimize your own cost. So you want to minimize the sum of C sub t of X sub t and ut. And as a benchmark, you want to compare yourself or your solution or your cost against some policy. So some policy within a policy class. Okay, so capital Pi is some policy class, let's say, and I want to compare sort of how well my controls have done, sort of with respect to some policy inside a policy class. What's here on the right hand side, let me just make something clear. What you have is a counterfactual notion of regret. So what you're trying to compare against is, in hindsight, having observed all the sort of like W sub t is in some sense what is the best policy inside the policy class, and then sort of execute that policy under the same state evolution that you sort of went through. So it generates a new sequence of states. It cannot be the same sequence of states because a different policy is being executed, and sort of you want to compare against this kind of uh, a policy regret metric. Okay, so this is what sort of differentiates it from, say, standard online learning, where this counterfactual notion changes the sort of state that you're visiting when you're sort of comparing yourself to the optimal. Okay.
Sorry, I have one quick question. So the WTs here are shared between the comparator and the learner?
Yes. So that's an assumption that we make on the system. The WTs are indeed shared between your cost as well as your comparator. So since this was brought up, let me just sort of say what we want to do. I didn't sort of define what we want to do with W sub t's. I didn't say how they were generated. So basically, we want to bound this regret notion with respect to all possible W1 to WT. Okay, so the only assumption that we're going to make on the W's is that at each step, it is bounded, say by 1. But of course, this could be any number. So we're going to assume that at each step, W sub t is bounded, but otherwise it's a totally arbitrary sequence. And indeed, it's the same WT that's being used in sort of the cost that you're suffering and the comparator that you're considering. Okay. So as I said, sort of let me just remind the setup. These costs are assumed to be convex. We are assuming the system to be a known time invariant system, and sort of we are assuming full observation. So I'm just going to take a few more seconds to leave this up there in case people have questions about the setup.
Well, so are you restricting the policy class?
Yes, so I'm going to do that. So I mean, this is a very general setup that I did. I haven't yet spoken about the policy class that I'm going to be working with. Okay, so this is in general like a game for any policy class, and now I'm going to sort of restrict the policy class that I'm going to work with. Okay, so that was a good segue to the next slide. What is a reasonable comparative policy class? And sort of thinking about this a little bit, one kind of sort of reasonable policy class is to compare yourself to the class of linear policies. So for things like when the noise is Gaussian, we know that in sort of the infinite limit, or in as t goes to infinity, and sort of the perturbations are drawn in from a Gaussian distribution, the optimal thing to do is basically just play a linear policy. So that's a reasonable policy class. This is sort of where we started off our work with. We wanted to capture linear policies. And sort of what we do is a slightly more general version of this. I'm just going to describe that now. Sort of a slightly more general notion of a linear policy is to have a notion of linear dynamical controllers. So herein you can sort of assume that like your controller itself holds some state, and sort of like, it by itself internally is a linear dynamical system. This is sort of not that relevant for maybe this talk, but this kind of thing turns out to be optimal when you sort of have partial observation. And the precise policy class that we are going to work with is a generalization of the above two. This is known as disturbance feedback controller. So let me describe this a little bit more carefully. So this policy class essentially uses as as input the disturbances or the perturbations that you've seen in the past. So suppose you're making a decision at time t, you sort of look at all the disturbances that have existed from W1 to WT minus 1. And what you do is you parameterize your policy by individual linear functions on these disturbances. Okay, so your policy is given parameterized by matrices M1, M2, all the way back. And the action that you're going to play is just going to be a sum of of this matrix multiplied with this. So it's a linear function of these disturbances. Okay, so let me just be a little bit more clear. I mean, this is just a linear function. We can also handle affine functions, and in fact, all results hold for affine functions. But just to be clear in this talk, I'm just going to leave it linear. Okay.
We actually have a question from the chat, if you wouldn't mind.
Sure. Yeah, please.
Quick interruption. Miriam asks that, or points out that linear policies with a fixed k are optimal for infinite horizon LQRs, but not for finite horizon.
Yes. I mentioned that as t goes to infinity, that's only when these are optimal. I should have mentioned it before when I said the optimal thing. For finite horizon, indeed, that it's not true that they're the optimal one.
So is there any way to motivate the fixed k assumption?
I guess the sort of easiest way to motivate the fixed k assumption, I mean, you could sort of like, if indeed sort of your, like, this is a fixed system, so if your game is sort of is going to be a long-term game, in some sense it should start to approach like a fixed k thing. I guess, I mean, okay, so sort of the easiest motivation I guess I have for this thing is that anyway, we sort of work with a more general policy class than a fixed k. And I guess, I mean, okay, so we are shooting for a very strong notion of potentially having sublinear regret, and like this seems like, for instance, like this is the first step towards sort of making something like that happen, and something like, and that's sort of a very natural class in that sense is the linear policy class. This kind of thing, as I said, like it leads to a generalization anyway of two linear dynamical controllers. Indeed, it might not be optimal for any sequence of noise. It might not even be potentially the optimal. I guess the way to think about it is like, you know, like let's sort of treat this as a comparator and derive a potential algorithm, and sort of that's our hope in some sense. Yeah, I guess that's sort of the best motivation I have. And of course, as t, if you have sort of t going to infinity, then it kind of captures sort of what the default thing to do is.
Right. One can hope that linear policies are would be performant, and in that case, this sort of notion of regret and this comparative.
Exactly. Okay. So moving on. So let me just quickly show why sort of this notion of disturbance feedback control is more general than linear controls. This is kind of not very hard to say. The way this comes out is if you just look at the law sort of that governs the control action, and if you just open it up recursively with respect to each time, what you see is sort of everything kind of just opens up, because everything depends on like everything is interdependent, and the only thing that sort of just remains is indeed just the perturbations. And sort of like if you just open it up, you get an expression that just looks like this. Indeed, the sort of controls that you're playing at any point of time, they're not a linear function of the k, but they indeed turn out to be linear functions of the perturbations. Okay, so if you sort of just relax this k times summation a plus bk to the I matrix into one of the MIs, it is easy to see that the control that you're basically just playing is captured by this class of controls. Okay, this class of disturbance feedback controls. Okay, so let me just go ahead and state the result. Our main result is that we provide an efficient algorithm such that for any sequence W1 to T, the regret notion that I had defined before with respect to the policy class of disturbance feedback controllers is bounded by order of square root t. Okay. So let me just say what I mean when I say things are efficient. The algorithm is going to remain polynomial in system parameters. It's going to remain logarithmic in time with respect to its sort of implementation. And something which I'm going to clarify in a little bit, we also need certain amount of stability notion from our system, and I'm going to define it precisely what we need. But as long as that is satisfied, which is something which is not extremely strong, it's something mild, and something like this should probably hold, like you should have that to have something sort of to get something like this in an O of square root t regret in something which is truly online and adversarial, right? So the costs are also adversarially chosen. So that's the result. That is the regret bound. I'm hoping to sort of show or at least convey all the ideas behind sort of how we get this regret bound.
Just let you know, you have about 5 minutes left.
Oh, that's it?
That was a half-hour talk. But there'll be plenty of time for discussions afterwards.
Okay, sounds good. So let me just quickly go ahead. So essentially, oh, sorry, I didn't have a clock in front of me, so I should have. Okay, anyway, so let me just convey sort of the main ingredients of the result. So the first ingredient is sort of convexification. Here, the problem by nature becomes non-convex if you parameterize it in K. Okay, so like we said, if we look at the equation of how the action looks like with respect to K, this is clearly a non-convex function of K. And this relaxation that we did to sort of disturbance feedback control, this makes the problem sort of very like the as a function of M, my control is just clearly a linear function. And sort of if you roll this idea out, what you get is the state that you're going to reach if you're going to play the sort of the same policy which is given by this M over time, that also looks like a linear function of M. So this overall thing as a function of M looks convex. So essentially what we've done is that sort of the hard problem of sort of even just the non-convex problem of the offline optimal, which looked immediately non-convex, we've sort of converted into a convex problem. And so what we can do now is sort of just change our game to be with respect to these M matrices. So the blue player basically just plays M matrices at a sort of T matrices at every point of time. And the action is chosen by this sort of policy. And again, sort of we can now define a policy regret, which is in the same fashion, which is this counterfactual notion. But sort of there are two immediate hurdles that you come into. Now I sort of need to have potentially too many parameters because my time goes back all the way till sort of till the start of time. So I need potentially t many parameters. And the second notion, the second thing is that it's still not reduced to say something like an online convex optimization problem, because the counterfactual notion still exists. So the state that sort of you reach depends upon everything you've done in the past. So we sort of have this counterfactual notion, and we will sort of deal in the next sort of things with both of these issues. So to get sort of rid of the number of parameters in the system, we're going to assume that there exists some. So this is the stability assumption that we're going to make in the system. This is called strongly stable systems. What I'm going to assume is that there exists some linear policy such that A minus BK has a spectral radius of less than 1 minus delta, where delta is a small constant. Sorry. And as long as I'm given access to any stabilizing linear policy, what we can show is basically that if you look at an action that looks like k times xt, plus sort of something that has a finite horizon of sort of past perturbations. So if you only hit it with a linear function of past h perturbations, as long as h scales as something like log t, and you've got this stability thing, h will of course be inversely proportional to delta. This can sort of emulate any stable linear policy. And as long as this K is a stabilizing matrix, you can also show that any disturbance policy is stable. So what do I mean by stable? In some sense, what it means is that sort of what you did sort of beyond 8 steps in the past does not affect. Okay, so it's in some sense, it's a bounded memory system. Okay, so that's what stability does. And with stability, sort of this game that sort of we needed to predict M1 till MT reduces to just being able to predict M1 till MH for H something like log T. So of course, we've now reduced the number of parameters in the system, which is logarithmic in time and potentially polynomial in the parameters of the system. The only little component left now, which we sort of need to care about, is that xt still depends on past actions. And this we sort of deal with again using this notion of stability. And the main idea here is that sort of stability, as I said, implies that only past h many actions matter. Nothing before that is going to matter. And sort of to deal with this, in some sense, what you can is we use this reduction into a different framework called OCO with memory, which was introduced by Anava et al. And the idea is the following. This will take a minute, and that's probably the last minute I'm going to spend. Essentially, what you're going to do is that the cost at any point of time, which depends on the state and the control, since everything about the system, due to the stability nature, only depends on what you've done in the past 8 steps, sort of the cost that you're paying at this point of time is just some function which remains convex in this case of the past h decisions that you've made. And remember, each of these decisions are of the type playing something from a disturbance feedback policy. So it only depends on the past h things that you've played. And this was exactly the kind of setup that was considered in this OCO with memory framework, wherein you're playing a game similar to like a standard OCO game, but the cost function that the adversary provides depends not only on your present action, but rather a finite window of size h of your actions in the past. And what you compare yourself again is with respect to something that's a static sort of static decision from your decision set. Okay, so in this case, you can sort of show that like if you've got a setup like this, all you need to do is an algorithm that resembles basically gradient descent. What you do is at any time, at any point of time, you sort of play a gradient step on this proxy cost function. Okay, so you sort of take all of its components, set it to the same value, x, 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 let's say, and then you just take a gradient with respect to x, and that's what you sort of propagate your gradient descent algorithm with. And essentially the idea is that sort of this sort of exploits the slow moving nature of OGD and Lipschitzness, so to sort of get this O of square root t bound. So that's so this is kind of the algorithm. Basically, you're just creating these sort of cost functions, which are sort of the cost that you will suffer right now, sort of based on what h actions that you've sort of proposed. This proxy cost function essentially just does, imagine you went 8 steps behind, you sort of played the same policy for 8 steps, look at the cost that you're sort of suffering at this point of time, take a gradient with respect to that cost, and then just move on. Okay, so that's it. So that's what sort of gives you this result. I guess I'm out of time, is it?
Yeah, if we don't mind, maybe we should take questions at the end. But thank you. That was really interesting. I've been meaning to look into this line of work more recently.
Okay, let me just
before
let me just quickly say something. I guess I can say this in the discussion as well. There is code available. Please do this controller. We sort of put it up as part of this at this link. So feel free to sort of play around with it.
Great. Thank you.